No, sir.
Okay, so let me move on and discuss a kind of very unrealistic system, but something that is has a lot of applications because usually, so we are going to treat a specific heat of a system which consists of particles with only two levels. So the system has no other degrees of freedom other than particles which can be either spin up or spin down state, and they're not interacting with each other. Usually that doesn't happen. Usually particles will have a spin degree of freedom, but they will have other degrees of freedom. Inside a solid, there will be vibrations and there'll be other degrees of freedom, and these are called phonons. But here we are ignoring all of that. So here we are going to a system of particles, a system of particles with two levels. We are discussing a system of particles, a system with two levels, right? So for example, this could be, let's say, spin half particles. There could also be like, if you have a lattice, and if there is like an atom in a place, in a site, that could be energy zero. And if it's missing, if the atom is missing, that could have some energy delta, right? Plus. So what we're going to assume is that it doesn't matter what the realization is. What it's important is that each degree of freedom has two states. One we are going to call spin up, another one is spin down. And the energy associated of each particle, so the individual particle, is zero, and the energy spin down is zero. It's traditional, and the spin up is delta, or the other way around. It doesn't matter. So if the number of particles in spin up state is n spin up, the number of particles spin down, and their total is n, then the energy of that state is n spin up delta, okay? Now, what are the number of configurations for n spin-off particles? Well, we know this. This is just given by the binomial distribution, right? This is one of the first things we did. And this is going to be factorial n spin-up factorial, n minus n spin-up factorial, right? Remember that? So the entropy of that state, or whatever the energy is, will be KB log of n factorial, n spin up factorial, n minus n spin up factorial. Now we can use because we are going to assume that we are in the thermodynamic limit, we can use Stirling's approximation formula and say that the log of n factorial, of course, the log of n factorial, we know that this is equal to. So I'm going to give you a quick derivation of Stirling's formula here. This is just nothing but the sum of n terms, right? Because these are all multiplication from n to 1. So this, for large n, can be approximated by an integral from 1 to n of log of n dn. And if I do this integral is n log of n minus n, and the limits are from 1 to n. So this gives me n of log of n minus n plus 1. This is a crude approximation. So all these, right. So what we get is that so using Stirling's formula, we can approximate the entropy of this configuration to be, well, it has some complicated expression, but it simplifies considerably. So this is the, and the detailed calculation, you can figure it out. Plus it'll be given in the lecture notes. Just a couple of lines of algebra. So we end up with an expression for entropy, which is nkb 1 minus E divided by n delta times, so this is in a bracket, log of 1 minus E by n delta plus E by n delta log of E over n delta. Okay. So when the energy is 0, then the entropy is 0, right? Because when the energy is 0, this term goes to 0 because x log of x goes to 0 as x goes to 0. We have to take that limit, right? Because otherwise log of 0 is infinity, minus infinity, right? But the way we evaluate terms like this is that we take this limit where x goes to 0. And x will go to 0 much more rapidly than log of x will go to 0. Therefore, this combination will go to 0. Okay? And this thing has, if E is 0, log of 1 is going to be 0. So we get, and of course, this makes sense, perfect sense, because, like when the energy is 0, that means that all the particles are in the down state, right? And that means that there's only one configuration. And this, goes back to the question that somebody asked at the beginning of a lecture where, whether you can have the entropy of a system of particles be 0, right? So it's,
So
that is
can it refer to the third law in some way?
I mean, not yet, because we haven't defined temperature in the system yet.
Oh yes, and
Okay.
also this is an unrealistic system, I guess.
Yeah, so we haven't really, I mean, it is a component, I mean, yeah, so, but, we are coming to temperature very soon. So the maximum value of the energy is when all the particles are in spin-up state, which is n times delta. Again, in that case, there will be only one configuration. And therefore, S of E will also be 0. And you can see that in that case, this thing is going to go, this guy is 0, and yeah, and over here, this is log of 1, which is 0, right? So we can plot what the entropy is as a function of energy, right? So we can plot the entropy as a function of energy, and here we have 0, And over here, we have the maximum energy, which is N delta, and in the middle, okay, let me just first. Okay. And so this is the half point, which is N delta divided by 2. So we see that the entropy is maximum which is N of KB of log of 2 when E is N delta by 2. Okay. Now, it's interesting to ask, what is the temperature at that point? So if you look at the temperature, it's 1 over del S by del E. So here, over here, when you reach the maximum entropy, what is del S by del E? It's 0, right?
Mm-hmm.
So that means that this is reached at temperature goes to infinity, right? At very high temperature. At very high temperature, half of the states are full and half of the states are empty. Now you might ask, what happens in this region? So in this region, temperature is negative. And this is an this is an unphysical region. Just because its temperature is negative doesn't mean that it's an unphysical region. So the interpretation of negative temperature is that as you increase the energy, the number of available states is decreasing. That is the interpretation of negative energy, right? And sorry, negative temperature. Because when we think about temperature, what do we intuitively think? We think of particles, say, zooming around. As we increase the energy, what is the available states of the particle that it can occupy increases. And to do this, you actually have to go to phase space, and you can show that in phase space, particles with more energy will have more area to fill out in. Okay, so our intuitive notion of degree of freedom, the state configuration, the number of configuration versus energy is such that as you increase energy, there will be more and more configuration for the particles to have access to. But for the two-state system, because the number of total states accessible is actually limited, it's actually finite, at some point, as you increase the energy, the number of states that is available, the number of configuration that's available actually decreases. And that's why this region has negative temperature. Okay. So I need 5 more minutes to finish this off. Should I do it, or should I postpone it until next class?
Sir, I think I still didn't understand the interpretation of the negative temperature. Could you explain it later if you get some time?
Yeah, I mean, I can do it again now. I mean,
okay.
Yeah. So the negative temperature is, whenever, whenever this thing is negative, right?
Yeah.
So that means that as you increase the temperature, the entropy decreases.
Right.
So what does that mean? That means that as you increase the energy, the number of configurations of that energy is decreasing.
Okay.
But that, usually when we are thinking of in the macroscopic world, when we are thinking about particles and we are giving them more and more energy, they can have more configurations, right? That's the intuitive understanding. And therefore, our normal intuitive understanding of temperature is that it should be a positive quantity because as we give more energy to the system, the number of accessible states is increasing.
Mm-hmm.
But here we have limited ourselves to a system where that is not the case, where,
Yeah.
so therefore, that's why it gets, so whenever you have a system where the number of total states is limited, and at some point, as you increase energy, you get less and less accessible states,
Mm-hmm.
configurations, you basically get negative energy. That's I'm not exactly sure how it will feel to your skin, negative energy, but it lies beyond infinite temperature. So not negative temperature, it lies beyond infinite temperature, right? You
Yeah.
have to go through
Past
this
that.
region. Okay.
Mhm.
But it has a formal interpretation without going into that region.
It
You
does?
could have just like, yeah, it just
Oh,
means that what I just told you, negative temperature means that as you increase your energy, the number of accessible states is decreasing.
oh, okay, yeah.
Okay.
So even under this definition, t less than 0 is an unphysical idea. Is that right?
No, I don't think so. I don't think over in this system it is unphysical because you have to go through t equals to infinity to get there. But by itself, negative temperature doesn't have to be unphysical. It is unusual, but it's not unphysical.
So that seems to say that our classical notion of temperature is limited in some way.
Yeah, yeah. I mean, you're essentially what you're doing is that you're analytically continuing the notion of temperature to a region where our classical notion is not valid, right?
I see. That's interesting. Yeah.
Yeah. Okay, so now what we can do is that we can actually look at explicitly what the temperature is for this system. And the temperature, if you do the calculation, I'm just going to spare you the calculation. It'll be given by KB by delta log of n delta by E minus 1. And you can invert this, and you can get the number of particles in the spin-up state over the number of total particles is given by, so this is basically E divided by delta N, and this is given by 1 plus E, let me just write it the other way. It'll be given by 1 over 1 plus E to the power delta by KBT, okay? So this is the distribution for this thing. Now, the last thing I wanted to mention is the heat capacity of this system. So if you calculate the heat capacity for the system, you find something very interesting. And you find something which has a bump in it. So if you plot this, you find that at low temperature, the heat capacity goes to 0 exponentially fast. So this is T, and this is the heat capacity. At low temperature, it goes to 0 exponentially fast, and then it increases, and then it goes to 0 at high temperature very, very slowly. And there's an interpretation for this behavior, and the interpretation is that um, just one second. Yeah. So the interpretation is that at 0 temperature, because there's an energy gap, right, between the ground state and the spin up state. So at 0 temperature, because of that, this is energy gap, as you increase the temperature a little bit, you don't really get to increase the internal energy. And therefore, the heat capacity at low temperature is 0. At high temperature, we saw that half of the states are filled and the other half are already are not full. At very high temperature, delta is, the temperature is much greater. KBT is much greater than delta. And therefore, the distinction between what is a spin up state and what is the spin down state is no longer valid. And so that's why it's hard to increase the internal energy at high temperature by increasing the temperature, right? So that's somebody wants to join. Okay. Okay. So that's why it's and in the middle, in the region where the temperature is of the order of the energy gap, that's when you get the most efficient way of increasing the internal energy, and that's where you get a bump in the heat capacity. If you look at realistic systems, it turns out the heat capacity is usually of this form. Okay, the heat capacity is of this form. That is, it actually, once it goes up, it never comes down. But because of this bump in this system of two level particles, this is known as an anomaly. Okay, it's like the anomalous expansion of water. That's not what you usually see in every other material. And this anomaly is known as the Schottky anomaly. Okay. So I think this is it. I don't think I have more things to talk about today, but do you guys have any questions? Well, if not, let's conclude this here, and then there'll be a from I think chapter 1 to 4 graded quiz on Thursday, and there will be and of course there'll be a class on Thursday. Okay.
Okay, sir.
All right. Well, thank you very much, everyone.
Yeah.
Thank you, sir.
Goodbye.
Bye.
Assalamu
Sir. Welcome.
Good evening.
Good evening.
Sir, the quiz is